Now we are going to test for the ratio of the two variances. So test for variances. So we are going to import these, and probably we can make use of the same sample steps. So import numpy, you will also import stats, and your, maybe let us write sample 1. Sample 1 is from normal distribution. You are taking a sample with mean 5, variance 4, and sample size would be 20. Similarly, sample 2 here again would be of, suppose it is, we can change here, we can make it 5, mean can be same, and here let us make it 3 and 20. Okay. Now suppose in this, let us consider the two-tail test, because we have been working with right tail test for the previous two-tail test. So we have to define the function first. Two-tailed variance test. So here it would be sample 1, sample 2, these are the arguments, okay, and alpha value would be 0.05. Now you have to write what will be variance 1, right, sample variance of both the samples, right? So variance 1 and variance 2, these can store your variances. So it would be np.var sample 1 comma ddf as 1, and the other one same way, np.var sample 2 ddf as 1. Okay, so we have calculated the sample variance S1 square, and this is your S2 square. Now what is your F star? F star is basically the ratio of these two. So variance of 1 divided by variance of 2, right? Then you have degree of freedom also, df1, df2 also. So df1 would be the length of the first sample. So that we already have as 20. You can directly reuse it, or maybe you can give this command. So length, this n1 minus 1. Okay, so note that here it would be minus 1, and here also it would be minus 1. Lower critical value lower would be stats.t.ppf alpha by 2 and degree of freedom 1 and degree of freedom for the second one, right? n1 minus 1 and n2 minus 1. Likewise, so here we are focusing on the F distribution. So it will look at those values which are less than alpha by 2 to the left of that, and similarly critical value for upper tail. Here upper tail here would be 1 minus of alpha by 2, okay, and it will be returning F star, and it will compare if F star is less than equal to your critical value, that is the lower critical value, or F star is greater than equal to the upper critical value, right? So in this region basically we reject. If F star is less than your F1 minus alpha by 2 and it is greater than F alpha by 2, so in that only we accept, otherwise we reject. So once you have defined the function, you can call this function and print the result. So result would be calculated using this function. And let us print the two-tailed F statistic, it is F star, and you are going to reject H0. So let us see what it prints. It would be the result over here. So the test statistic value comes out as 0.981, and you are going to reject the null hypothesis because that is true. Okay, it means it falls in the rejection region, and you reject the null hypothesis if your F statistic is less than equal to F1 minus alpha by 2, or if it is greater than F alpha by 2. Okay, so this is how you can test for variances. This is just for two-tailed. Likewise, you can write for one-tailed, and which includes right and left-tailed. So you can do it accordingly. Next, we will look for the test for proportion. So import this numpy, and sample 1 here would be np.random. So it will going to select. It will take values between 0 and 1. 0 and 1, not between. It will take values 0 and 1. Size here would be 100, and the p values would be 0.3 and 0.7. Okay, so it means it is going to generate a random sample of 100 observations with two possible outcomes, that is 0 and 1, and the probability of choosing 0 would be 0.3 and probability for choosing 1 would be 0.7. So basically this would simulate a binary outcome like a coin tossing or pass or fail test. So likewise you can define for the second sample also. So we can reuse this. So here we can take the sample size as 120, and let us change the probabilities 0.4 and 0.6. Okay. Now if I have to conduct a right-tailed test, suppose, then I need to first of all define a function, right-tailed proportion. So here it would be sample 1, sample 2, these are the arguments that we give. P0 will be the hypothesized difference of the two proportions, and alpha here would be 0.05. So we can calculate your P1 hat, P2 hat, that is the sample proportions. So here we will reuse this mean command from the numpy library, sample 1, and again np.mean sample 2. So n1, n2, so n1 would be the length of the first sample, and n2 would be the length of the second sample. Once you have written this, now you can find the test statistic, which is basically the difference in the numerator. If you can recollect, it is P1 hat minus P2 hat minus the hypothesized mean difference, that is P0. In the denominator you divide by the standard error. Okay, so let me mention the numerator first. It would be P1 hat minus P2 hat minus P0. It will be divided by square root of this. So here it would be P1 hat into 1 minus P1 hat whole divided by n1 plus same thing for P2 hat also we will have P2 hat 1 minus P2 hat, it will be divided by n2. Okay, So now you will calculate the critical value. Stats, because we know that here we can use the normal approximation. So stats.norm.ppf, the percent point function, here it would be 1 minus alpha, and it would return the z star value, and it will compare the z star if z star is greater than equal to your critical value. Okay, so finally we can call this function. Result would be P naught I should have defined here. P naught would be, suppose it is 0.1. So let us see what is the z star value. It is minus 1.73, and the result that you are getting is false. It means you fail to reject the null hypothesis. Okay, and since it is a right tail test, you fail to reject the null hypothesis. It means that the difference of the two proportions, that is P1 minus P2, is going to be less than equal to 0.1. So your null hypothesis, basically the claim is correct. So this way you can perform different tests whenever you have two samples also. So we have seen for difference of the means, for the ratio of the two variances, and for the difference of the two proportions also. Now we are going to look at chi-square test of independence. Chi-square test of independence. Okay, so we can import numpy as np, and from scipy.stats import chi to this contingency. Okay, so basically it has this nice function already defined in scipy.stats, because here you can directly use this function from this module in order to perform your chi-square test of independence. Okay, so let us consider the observed data is, let me just mention, observed data is in the form of an array. So here we have (40, 50, 30) suppose. Then the next one suppose is 50, 30 and 40. We can take 10, 40 and 10. So these are the observed points. Okay, so basically we have written it in the form of a matrix. Okay, so these are basically your observed frequencies in each category for a chi-square test. You can see that it is like a 3 by 3 matrix format. Okay, so observed data is given to you. So it means you have two categorical variables and each of them have 3 levels. Now you're going to perform your chi-square test of independence. So it is easy to do that because we already have that function. Now p value will also be computed, degrees of freedom would be there, and what will be the expected frequencies here? We will use this function on observed data. Okay, so here this chi2, and this is a test statistic for the chi-square test. P value will be used, then it will indicate the probability of observing the data if the null hypothesis is true, degrees of freedom for that test, and the expected frequencies, which are calculated based on the observed data assuming that the null hypothesis is true. Right? Now you can print your results. If you want to print, suppose, your chi-square test statistic and all of them. So maybe we can just first of all check if the p-value, if p-value is less than alpha, you will print what it will print? It will print reject the null hypothesis. Reject the null hypothesis. There is a significant association between the two categorical variables. Okay. Else what it will print? Else print fail to reject. No significant association. Sorry, it should be p underscore. So yeah, if I should just compare it with 0.05, or I could have defined alpha beforehand. So you reject the null hypothesis, there is, and conclude that there is a significant association between the two categorical variables. So here you're rejecting the null hypothesis. It means that the p-value that you have obtained is less than 0.05. So if, let us see what is, okay, so it's very small. Okay. So these are your expected values. Okay. So these are your observed, and you can see that this is how you get your expected frequencies. If you want to give a proper print command, you can give for the chi-square test statistic. First you can give, then print p-value, print the degrees of freedom, print the expected frequencies, and then you can print this expected, or you can just directly see what is happening over here. So this is how you can perform your chi-square test of independence by just simply using this function from scipy.stats module. So it is easy. Likewise, let us see for chi-square goodness of fit test. So import numpy as np, that will be there, and from scipy.stats import chi-square, because we are going to deal with the chi-square distribution. Now let the observed counts can consider 40, 30, 30, suppose. These you can consider them as the observed count, suppose for the three colors, maybe red, green or blue. Okay, then what will be the expected proportion? Maybe I can just remove this. So expected proportion would be what? NP. So here 1/3 for each of them. Okay, so we are not biased towards anyone, so each of them have an equal proportion of occurrence. NP dot array. So here now what will be the total number of observations? Total observations will be NP dot sum of your observed counts that you have over here. Okay, and your expected counts, E is calculated by multiplying n, that is the total number, by the corresponding PIs. So these are your PIs, expected proportion. For each of them it is 1 by 3. So here it would be total observed multiplied by expected prop. Okay. So first you have the observed counts, then you have your expected proportions for each event under the null hypothesis. Okay. So we are assuming that each event is equally likely. So proportion is 1 by 3 for each of them. Then here we are calculating the total number of observations. We sum up all the observed counts, and expected one will be calculating the expected counts for each event based on the total observations and the expected proportions. So you are going to multiply them in order to get the expected counts. Okay. Now you can perform your chi-square test. So chi2 stat and the p-value. So here we will use this chi-square function, chi-square. So f observed these would be the observed counts, and your f expected would be the expected counts. Okay, so if you want to see these, it is t, and your p-value over here is 0.367. So obviously if you take alpha as 0.05, you fail to reject the null hypothesis. Okay, so if you fail to reject the null hypothesis, it means that the observed distribution does not differ significantly. Okay, so you can write the command for comparing p-value with the alpha value as we have done here. Okay, so this is just a simple scenario that we have taken. Obviously you can think of it for different situation where you will be altering this observations over here. Okay, so likewise you can get the answer, and you can see that finding these is very simple, right? And in fact the theory behind them is also very easy to understand. So this basically completes your week 9 for hypothesis testing. In the next week you are going to learn about bootstrapping and how do you do or perform hypothesis test when the population is not necessarily normally distributed, right? It might be coming from some other distributions, or you might not even have an idea that from which distribution is it coming, right? So in such situations we use bootstrap technique, and that we will cover in your week 10. And in the last 2 weeks we will be talking about confidence interval estimation. Thank you.